Hello and welcome to the lecture Autoregressive Generative Models. In this lecture, we are mainly focusing on autoregressive models. First, we start with fully visible belief network. Then we discuss two major networks, pixel CNN and pixel RNN, which of autoregressive type. Today, we'll start autoregressive generative model. Autoregressive generative models generate data one element at a time. That each new element is predicted based on the elements generated previously, and that's the name autoregressive. They model the probability for a sequence x1, x2, x3 up to xn, that this is the probability of this is p of x1 multiplied p of x2 given x1. That means x1 is already generated. Upon generated x1, what is the probability in x2? Again multiply that, giving that x1, x2 have been generated, what is the probability x3 and so on. So xn, which is x1, x2, x minus 1, these are already generated, and observing this, what is the probability of xn. So autoregressive in that way, that the whatever is generated is used to generate the next token or next probability. So the model learns conditional probabilities of step. Okay. Common examples include GPT-style language model, pixel CNN, WebNet, etc. They are widely used in text, speech, music, and image generation. So this is a very naive definition of autoregressive. Now, how it works? The model receives an initial input or prompt, okay, and it predicts the probability distribution of the next element or token. That is the basic idea. One token is selected from its distribution. The selected token is added to the sequence. The process repeats until the desired output is. For example, here, the input is the cat is. Now, model predicts by observing this, the previous tokens is the cat is, that model predicts sleeping. The whole statement is the cat is sleeping. That's why the next token will predict. And it continues until the sentence is complete. So this is where the autoregressive model basically works. Now here, for an image example, an image is converted into a sequence of pixels, patches, or tokens. Okay. Here you can see these are the patches. The model observes the previously generated elements, and then it predicts the probability distribution of the next visual token. Upon this, can get the next. A token is selected and added to the sequence. So when it's generated, this process continues until the complete the image. Sometimes it is a fixed encoding and unnatural rasters can happen, or our variable encoding, natural effective codes to find. So these are the way it has been basically predict the next tokens. Now, what are the major advantages of autoregressive model? That it easily captures complex spatial relationship between image components, and it provides a clear probabilistic framework for image generation. So can be conditioned on text, labels, or other images. It can generate diverse and realistic visual content. On the other hand, there is some drawback of autoregressive models. That sequential generation can be computationally expensive also. That is one of the major aspects. Large images require many tokens, or high quality generation may require substantial training data and computing resources. So these are the advantage and disadvantage of autoregressive models. Now we will discuss the fully visible belief network. Now this is the explicit density model. That is, the likelihood image X is basically a joint likelihood of each pixel in the image, P of x1, x2, x2. That is basically way to understand. The single image X is basically joint probability of all the pixels. Okay. Now a fully visible belief network is an autoregressive probabilistic generative model in which all variables in the input are treated as visible and joint probability distribution is factorized into a sequence of conditional probabilities, as we have seen here, that all pixels are visible, and it is basically that the probability of image X is the joint likelihood of the pixel of the image. So for an image represented as a set of pixels or visual tokens, for example x1, x2 up to xn, the model represents the distribution as this p of xi given x1, x2 up to xi into 1 to n. Now this is a multiplication. So first 1 to 1 at p of xi into p of x2 given x1 into p of x1, x2 given x3 given x1, x2 and so on. So the each pixel or token is therefore predicted based on only on the previously ordered variables, enabling the network to capture dependencies among different regions of image. For example, if we see this, that here what we are actually trying to say, that p of x is first p of x1 into p of x2 given x1 into p of x3 given x1, x2 and so on. So ultimately it is coming p of xn, x1, x2, xn minus 1. So this is the basically this multiplications. Now each pixel or token is therefore predicted based on all the previously ordered values. You see, x2 is being depend on x1. x3 is depend on x1, x2. And xk, if we say xk, x of k, it was x1, x2, dot xk minus 1. So this is a special case. So what is the previously ordered? This is the previously ordered variables, enabling the network to capture the dependencies among different regions of an image. Now here, if you see in this figure, you see kind of some kind similar kind of thing, that we start from here and we'll go here in this direction, then to here, then to here, so in this direction, and likewise. Okay, so this is the way we basically we do this particular thing. Okay, that these are the way it is being taken care of. Okay, now fully visible belief network typically trained using the maximum likelihood distribution. That's what we have seen in the last lecture. But the objective is to maximize the probability assigned to training. During generation, pixels or tokens are sampled sequentially according to the learned conditional distribution. That's what we have seen last slide. So the models such as pixel RNN and pixel CNN are prominent examples of this fully visible autoregressive approach. I will see later. Although this fully visible belief network provide an explicit and tractable likelihood assumption and can model complex image distribution, the sequence and sampling process can make image generation computationally expensive. Because see, all the patches have been, and the later stage, all the patches will be considered and definitely make it. Here, this is an explicit density model that we have seen. The chain rule is used to decompose likelihood in product of distribution that we have seen. And the goal is to maximize the likelihood of training. As neural network is used to mirror the complex pixel distribution. So this is the FVB, the fully visible belief. There are different kind of autoregressive model. For example, that pixel RNN and pixel CNN, that is for image generation. It is a very famous AI models. Then transformer, that is also very famous AI models for autoregressive generation. And the generative pre-trained transformers for text generation, that is also autoregressive in nature. Now we start with a very simple one. It is Aaron van der Rohe et al. From Google DeepMind, ICML 2016. It's called Pixel Recurrent Neural Network, this paper. So, Pixel Neural Network, or in short Pixel RNN, are deep generative image models that are designed to estimate the joint probability distribution of the natural image. Developed by Google DeepMind, as we said. This framework sequentially predicts pixels along two spatial dimensions to capture both highly local and long-range pixel correlation. Now in image, the pixel correlation are very important, and the pixel statistics is very important to model to understand the total image statistics. So here two spatial dimensions are captured, both highly local and long range pixel correlation. Sometimes local pixels are important for a particular patch of the image, whereas sometimes long-range pixel correlation is required to capture. The joint distribution over this n cos n pixels is equal to n square. Is an image X is factorized as a product of conditional distribution, as we have seen before. Right? Pxi given x1, x2 up to xn. The network scan the image one row at a time and one pixel at a time within each row that we have seen. Predicting the probability of the current pixel xi given all previously generated pixel x1, x2 up to xi minus 1. That is the basic. That is right. Now, not only this, within each individual pixel, there is the three color channels: red, green, and blue. Red, green, and blue are also factorized sequentially. For example, of xi, this I pixel of red channel, all I pixel people, I pixel of G channel, so I pixel of IR of R channels, and I pixel of blue channel, so all of I, that IR and IG. So not only in the sequential pixels, but also these channels RGB that is factorized sequentially. This means each color channel is conditioned on the other channel as well as all previously generated pixel image. That is the major aspect of this very important work by Google Ignite at 2016. Now we try to expand a few variants of here one by one so that you understand the whole work very easily. So first, very easy thing is pixel CNN, a very simplified, fully convolutional alternative of 15 layers that preserve spatial resolution and used masked convolution. That is very important. This masked convolution capture the bounded receptive bits. Now, what do we mean by masked convolution? Now, here you see that this is the pixel we want to predict here. Now, when this pixel we want to predict, all the pixels before we have generated are taken into consideration. But the pixels that are not generated, this one, this one, this one, you can see here that if this particular pixels has been already been used, this is used, this is used, this is used. So they all been generated. So it is used to capture this or predict this. But these pixels that it is not being generated, that 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 is not being used to participate to predict this. That is called masked convolution. So this is the convolution thing. You see, this 3 and 1, this is 1, right? But this pixel, this is the actual what we have to predict. But these are masked. These are masked. This is the masked convolution. Okay? Pixel CNN use this. So masks are adopted in the convolution to avoid seeing the future context. So these are the future context. These are the future context that we cannot see. So in addition, while generation while generation remains sequential, pixel CNN allows the complete parallelization of the pixel computation during training and evaluation. Because of this mask convolution, it can parallelize this. Because these are zero, so they are not anyway going to participate in the predicting process. So this is the basic idea of pixel CNN. Now, as we said, the mask convolution pixel CNN is a modified convolution approach used to ensure that when predicting a pixel, the model only use the information from the previously generated pixels and not from the future pixels. That's what we have seen. That they use these, but not is this, the future future pixels. In a standard convolution, filter can process all neighboring pixels. So in standard convolution, all pixels are taken care of or participate for this, which would violate the autoregressive property required for sequential image. That's why that pixel CNN applies a mask of convolution filters that sets the certain weights to 0, like this. Set zeros, blocking connection to the future pixel. Such pixels are right and below the current pixels. This ensures that each pixel is predicted based on the pixels above and below. So this is the idea. This is why how pixel CNNs work. Next come the pixel RNN. The pixel is by pixel is generated. As the process is started in general from the left to top corner. An RNN or LSTM is used to model a dependency on the previous pixel for the current pixel. So here that pixel is some RNN. Pixel RNN treats an image as a sequence of pixels and predicts each pixel based on the pixels that comes before it. As this is autoregressive. It generates an image by generating one pixel at a time. So this is pixel. Now there is a three basic thing: left, or center, or right. Left to generate pixel psi, one condition on the to the previously generated pixel left of the above pixel. Center is to generate a pixel in the multi-scale case, where we can condition on the subsample dimensions in the light blue. These are the center pixels in this way. And right, diagram of this connectivity inside a mask convolution. In first layer, each of the RGB channels is connected to the previous channels and the context, but is not connected to the itself. So you can say the mask, this is the mask and mask, that is, these are the mask part. In subsequent layers, the channels are also connected to themselves. So this is pixel RNN. That is where the context, the multiple context. Now, how actually it works? This is row LSTM. So these are this thing. Okay. A unidirectional layer that process the image row by row from the top to bottom using 1D convolution. That you can see. This is a row LSTM. The layers capture the roughly triangular context. So this is the triangular context above the current pixel, but is unable to capture the entire available context. That is row LSTM. Next. Then come the diagonal by LSTM, designed to capture the entire available global context. So here you can say this particular thing taken care. It skews the input map by offsetting each row one position. Here you can see. And parallelize calculation along diagonals, utilizing highly nonlinear 2 into 1 state to state combination. So this is called diagonal bilistic. So here you can see the three comparison between the three variants: pixel CNN, row LSTM, and diagonal. Here it is a max convolution. This is row LSTM, so LSTM is used here, and this is this diagonal bilistic. So what is the basic application? It is used for image generation, density estimation for images, image completion or inpainting, that pixel RNA is used, lossless image compression. So what is the major drawbacks of this particular one? Very slow generation, pixel by pixel. It's computationally expensive and very hard to scale for a very large pixel. So that is that. We can show some examples here and say here this is CIFAR10 database. Visual result is image data is basically generated using this pixel CNN and samples model trained on image method. This is image. So this is in summary. In this lecture we introduce autoregressive model, fully visible belief network, and pixel CNN. In the next lecture we start transformers. Thank you very much.